Right, so here this is your last half an hour of warm inside. So I'd like to talk to you a little bit about galaxy clusters, which is my area of research, well, broadly my area of research. And what I want to talk about to you tonight is how structures like that form and what we can build in galaxy clusters. So let me just start with a brief definition of what a galaxy cluster actually is. Without getting too technical, I'll put you a picture here of a galaxy cluster, not surprisingly. And that's essentially what it is. It's an assembly of many, many galaxies, several hundred to thousands, that generally speaking are gravitationally bound to each other. So, if you want to understand a structure like this, it's not enough to just look at pretty pictures. We actually want to understand how such a structure forms. How do all these galaxies end up in the same place? And to understand that, we need to talk a little bit about matter in the universe and how this matter is distributed. So all of you are familiar with the simplest form almost of matter, a star. You've seen that. If you are particularly lucky, you've already seen the Milky Way. And you obviously all know that we have many, many galaxies out there, which themselves are just huge assemblies of stars. 700 billions of stars in each galaxy. But this matter, so I'm just putting pictures up here, that's actually only a very, very small part of the mass in our universe. And if you look at what the universe is actually made of, well, I've got this little pie chart here, and most of it is something that's called dark energy. I will not go into detail here. It's a force that gets the universe to expand, accelerate expansion. But if you then look at the matter itself of the universe, we have the normal matter I've just shown you here. And the stars, we just had pictures of, well, that's a tiny, tiny fraction even just of normal matter. Most of normal matter, like matter as we know it, is a gas. Gas doesn't particularly glow or do much. It's there, but you can't actually really see it. And then there's this other part, dark matter, and that's the kind of matter which we don't see. We only know it's there because of its interactions. And if you have the kind of relation between dark matter and normal matter, it's about 80% dark matter versus 20% normal matter. So there's a lot more dark matter there than normal matter. And the way you can imagine this a little bit is like you're looking at an iceberg. And the tip of the iceberg is the matter we see. But most of it we don't see. And there's all this stuff, dark matter, dark energy, which is there, which shapes our universe very much. But we can't actually see it with our eyes. But if you get serious about galaxy clusters, and if you want to understand why galaxy clusters appear, we need to first understand how most of the matter actually is distributed. So, luckily, we can do that. We can understand how dark matter is distributed via computer simulations. And I'm just going to show you what we think the distribution of dark matter in our universe looks like. You arrive at a picture like this. Now what you see here is what we call a cosmic web. And that's just how we imagine dark matter to be distributed. And wherever it's yellowish, there you have the more dark matter, like denser parts of dark matter. And wherever it's dark, there's almost no dark matter there. And what we have here is very much these node-like structures, cells, which are connected by these filaments. This is a very intricate structure in itself here. And because there is so much more of this dark matter there than normal matter, actually, it shouldn't be a surprise then that normal matter follows dark matter. And the way you can maybe picture this in your head is, if you have a riverbed that shapes a landscape. That's like the dark matter. And the ordinary matter, water, that just follows that with a riverbed, the path that is laid out for it. And that's very similar how you can imagine how normal matter, galaxies, stars, actually follow this structure of this cosmic web that's laid out for them. And then, knowing that you have these galaxy clusters, which are these huge, massive structures, also then shouldn't be surprising that they actually sit in the most massive nodes of this dark matter. That's where you find galaxy clusters. And then you have smaller nodes all around, where you have individual galaxies, or maybe sometimes just smaller groups of galaxies that sit there. Now this is all well and good, and this is how it looks like today in our universe. But how does matter get to look like this? How does it get to distribution like this? I mean, we know the universe started with the Big Bang. You have the matter of the universe which starts expanding from that Big Bang. Very bad artistic expression here. And you'd expect, you know, if you have just, if you had a bucket of water and you just splash it out, you'd expect it just distributes more or less equally, right? This is, however, not quite what it is. Matter is not quite distributed equally in the universe, but there are small, tiny little density fluctuations, which I just have a little picture of here, how we see this. This is from the cosmic microwave background. I'm not going into detail here. But the way you can maybe imagine this whole thing is, you know, we've ever been out when it started raining, and you watched how the rain starts dripping onto the floor and makes the floor wet slowly. You may see that, you know, there are some patches which get wet a little bit faster than other patches. But just by chance, there are slightly more raindrops here than over there. And that's very much what happened in our universe. At the beginning, after the Big Bang, it just happened that there was little fluctuations, just by chance. Now, with rain, this evens out again, and eventually everything's wet, as you expected. But now, universe, we have this force, gravity. And this changes everything. What gravity does, as soon as it realizes there is a little bit more mass here than over here, this more mass starts pulling at the mass that surrounds it, and it acts to empty out spaces in the universe which are slightly less dense, and starts accumulating mass in spaces where there's a little bit more mass already. You can really imagine gravity just grab everything around it and pull it towards it. Now, a bit more scientifically, how this looks like. I'm showing you this video, which hopefully you will. And what you see here as a start is dark matter distribution in our universe just shortly after the Big Bang. And you can see it's mostly flat, but there is tiny little fluctuation where there's a little bit more in the center. Okay? As I just told you, this will start to attract mass. And this is what you will see as I start the video. We start off with small fluctuation, and very, very quickly becomes very structured and starts growing until we arrive at redshift of 0.
Catrina, I suggest you put the lights down a little bit because it's quite hard to see.
Okay, I can try to do that if I know where to do that.
Switches on the wall over there, where the little red light is.
You want all of them off?
I think that would be better.
Yeah, okay. Now I don't see you and you don't see me, so I'm going to take care of, right? Okay. So, let's have a look at this. Right, so you can see how very, very quickly structure became to form. Started to have this node here, which keeps accreting more and more mass. You just can watch that unfold as time flies. present time. So, this is how we get to galaxy clusters from tiny fluctuations of dark matter at the start. Now, this is all very great, and you may now stand there and wonder, why do we care? I mean, wonderful, we have a bit more galaxy over here than over there, so what? Is that important? Yes, it actually really is. For many reasons. Number one, many galaxies today, they actually live in a cluster or a galaxy group of some form, including our own galaxy, the Milky Way. And this has huge impact on how galaxies actually evolve. Can you imagine this maybe a little bit like, imagine you grew up in a tiny flat, let's say 5 siblings, all crammed into one room. Imagine somebody else who grew up on a huge farm, their own room, plus other rooms for themselves. You can imagine that these two personalities will be evolving quite differently, right? And that's what happens to galaxies too. In galaxy clusters, they're all crammed in one location. And that means they're going to evolve very differently from a galaxy that's somewhere out in isolation. But also, galaxy clusters are actually, because they are this dense environment, great laboratories for physics, particular cosmology, general relativity. I'm just going to show you a couple of examples of what I mean here. The first one is the discovery of dark matter, really. This was first postulated by this fellow here, Fritz Zwicky. He was a Swiss astronomer and quite a grumpy too. He worked in the US, and maybe because he was so far away from all the chocolate, the nice chocolate, he didn't like his colleagues very much, and he called them spherical bastards. And they were spherical because they're bastards no matter which side you look at them. But apart from that, he was actually also a really good astronomer. And he studied galaxy clusters. And when studying galaxy clusters, he was particularly interested in the motion of the galaxies, the individual galaxies, in this cluster. So he just looked at how fast they move, which direction they move. And what he found was something puzzling. He found that these galaxies actually move too fast to still be gravitationally bound to the cluster. So just to have an analogy here, to be bound to a system like our planets to the solar system, you can't be too fast. If one planet all of a sudden decides to really accelerate, the sun wouldn't have enough power anymore, enough gravity anymore to pull the planet towards it, it would just fly away. And that's what he found for these galaxy clusters, that these galaxies would just disperse if the situation is really as it is. So what he thought is, okay, if I look at this galaxy cluster and they're moving so fast, there must be something else there, something that keeps these galaxies together. And this something else, this extra mass that he thought was there, he didn't know what it is, so he called it dark matter. Now obviously these galaxy clusters, that's not the only reason why we these days believe that there is dark matter, but this was the first hint towards it. Nowadays we have many more proofs, so to speak, for its existence. Then the second thing, no, this is gone, that what we do with galaxy cluster is testing physics. And one example of physics we can test is general relativity. So Albert Einstein, back in his days, predicted something we call gravitational lensing. And the way that works is that he thought, if you have a background source, here, a galaxy for instance, and then some mass in between this background source and the Earth, instead of this background source just emitting its light in straight paths, as you can expect from light to go, this mass in between kind of gravitationally attract light, so it would bend this light. And we could see this effect on Earth. And that's what we call lensing. And not unsurprisingly, because Albert Einstein is always right, this is what we observe. And it's just to show you how this looks like. So when you look at images of galaxy clusters, it's these arcade-type structures, which are actually pictures, images of galaxies behind the galaxy cluster. This is actually not only cool because it proves Einstein to be wrong, right again, but because this effect depends on the mass in between, you can then also get a kind of profile, a model of which mass is there. And once you go at that and you subtract all the mass you see from this model, you know how dark matter is distributed in there. And that's quite a cool application of gravitational lensing too. Right, we're moving on to something even more important and closer to my heart is, I already hinted at it before, galaxy evolution. Galaxy clusters are very, very important for how galaxies evolve. And to give you an idea of what galaxy clusters do to galaxies, let me start by galaxy properties. The Hubble tuning fork, which probably a lot of you are very familiar with. Hubble has found, and obviously we confirmed that the galaxies look very different from each other. And we kind of aligned them in this sequence of different galaxies. But it's not just looks. It's not just that this galaxy looks different. They're actually measurably, quantifiably different from each other. And a way to look at that is something we call galaxy color. So if you look at the galaxy and we just count the light that comes from this galaxy, some galaxies look more blue than others. And it's really been observed that there's two distinct populations. There's a blue population of galaxies and a red population of galaxies, and not much in between. And this actually goes back to this picture I showed you before. You immediately see that these galaxies here look more blue than these galaxies over here, which look more red, right? So, with this in mind, let's think a little bit more about galaxies. I mean, it's not just colors and it looks different. That's still a bit like, okay, whatever. If you really want to measure out galaxies, which properties are important to measure out galaxies? And in extramolecular astrometry, there's two main quantities which we are really interested in. And the first one is what we call a star formation rate. So this just measures for a galaxy how fast does it form stars. So it basically counts each year how many stars have you formed. That's star formation rate. The second thing is the mass of the galaxy. So how many stars are already in this galaxy. And now you can start to tie those two properties to galaxies we observe. And it so happens that actually, if you have a blue galaxy, it's star forming, generally speaking. If you have a red galaxy, it usually is not star forming. We call that dead. So we have these two distinct populations: star forming blue galaxies, red galaxies, dead galaxies. Okay? That goes further than that. Second quantity, mass. Now we have found that actually blue galaxies are less massive than red galaxies in general terms. Okay? So while you still got forming stars, and that's probably quite intuitive, they generally have less mass than something that already stopped forming stars. So why am I telling you all of this? It's because in clusters you almost exclusively find this type of galaxies. So red galaxies that don't form stars anymore. Why is that? Why should a cluster kill the galaxy, so to speak? And to understand why this happens is you need to understand a little bit how a galaxy forms stars. I'm just going to go very briefly into this. a galaxy like this. And stars don't just drop out of the heaven and are there. They need fuel to form, and this fuel is gas. So if a galaxy has gas, this gas can organize itself in clouds. These clouds can collapse and form nice little stars. And as long as this fuel doesn't run out, the galaxy keeps forming stars. You can imagine it like a reservoir. But eventually, a galaxy may, for some reason, not have gas anymore and stop forming stars. Now, when you come to clusters of galaxies, these have not always existed as these huge agglomerations of galaxies as we know. But galaxies, because gravity pulls them towards this cluster, join the cluster gradually. So they kind of, what we call, fall into a cluster. It's just by gravitational pull. And as galaxies fall into a cluster, what happens is they get stripped of its gas. I kind of illustrate this here. These galaxies would be pulled into this cluster. They start losing this kind of gas. It gets pulled towards the cluster and pulled away from the galaxy by the mass of the cluster. So this, you can imagine a cluster really to be kind of this hungry beast. It eats the gas of the galaxy and takes it away from it. But obviously, as I told you before, when these galaxies run out of gas, it starts dying. It stops forming stars. And that's how, with time, as you fall into a cluster, galaxies turn from something like that, in blue and star forming, to something like red, and not star forming anymore. So really what galaxies do for you, and what galaxy clusters do for you, they turn galaxies dead, essentially. Right. I'm going to stop here and leave some time for questions.